3 p.m. in Beijing, and I'm happy to announce our today's speaker, Professor Xing Chen, will tell us about bner-Shirshov basis for the conjugacy problem of braid groups. So let's welcome.
Okay. My title is the global Shirshov basis for the conjugacy problem of braid groups. This joint work is with the Professor Moscow Liu, Hunan Normal University. I will introduce this paper for the 4 part. First, I will introduce the source of the conjugacy problem of the braid group, and then the word problem and of braid group and the global Shirshov basis. Then I will introduce the conjugacy problem of B3. Finally, I will introduce the main conclusion. This is the theorem about conjugate classes of B3. First, Artin gave the original definition of braid groups. It have A1 to an AN for there is a generator and some relation, and then Garside obtained an algorithm of the conjugacy problem of Bn with the fundamental word delta he defined. Then the braid group can be written as a semigroup.
I beg your pardon. When you write AI commutes with AJ, you should mention that I and J are far enough. AI does not commute with AI plus 1.
AI plus 1.
So in your presentation, you should indicate that AI does commutes with, yeah.
I forgot the I minus J should be 2 or more than 2, more than 1.
Yes.
Yeah. J cannot be I plus 1.
Yeah, sure.
Yeah, there is also the yeah.
Well, excuse me. Here you write that delta equals Pn minus 1 and so on P1. Well, of course I know what it is, but if you introduce new notation, you should. Okay, PK. Excuse me. You gave this notation. Okay, thank you.
Yeah. And then Alexander theorem point out that for each link, there exists a brand B such that the B, the closures of B equal the link L. That is shown in this figure. Here, this is the brand B, and this the closer of the brand B. This theorem connected the brand group theory and the link theory. And then Markov theorem. Then this is Markov theorem. Suppose beta and beta prime are two brands, but not necessary with the same number of brand strings. Then the closures of beta and beta prime present the same knot or link K if and only if B can be deformed into beta can be deformed into beta prime by means of a finite number of type 1 and type 2 Markov moves or the inverses. Namely, there exists the following finite sequence beta equal beta 0 to beta 1 to the beta m equal beta prime, such that for I equal 0 to m minus 1, beta I plus 1 is obtained from beta I by the application of a type 1 or 2 Markov move or the inverses. This is the Markov move. So we notice that the type 1 Markov move. That means the closer CL beta and CL beta prime represent the same knot or link if beta and beta prime are conjugate. This is why we need to solve the conjugacy problem of brand group. In fact, we need to first solve the word problem of brand group because the closures CL beta and CL beta prime represent the same knot and or link if beta and beta prime represent the same element in Bn. Therefore, we better use the same concise and convenient method to solve the word problem and conjugate problem of brand group, and even further solve the equivalence problem, which is corresponding to the type 2 Markov move. Then we can get a link invariant if this method exists. For any two words f and j, does there I will introduce the word I want to introduce the word problem. This is for any two given words, F and G, that there exists a feasible way to judge whether they present the same element in Bn. Example, given two words, F equal A3, A2, A1, A2, and J equal A1, A3, and A2, A1. That F and J represent the same element in B4. In fact, F equal A3, A1, A3, A2, A1, A2 equal A3, A1, A2, A1. And then A1, A3, A2, A1. This equal G in B4 because we know A2, A1, A2 equal A1, A2, A1, and A3, A1 equal A1, A3 in B4. But we should find a feasible way to judge whether they present the same element in Bn. Artin gave an algorithm for the word problem of brand growth, and then Garside provided a new algorithm with the fundamental word. And Bokut obtained a set of global social bases for the brand growth, which was corresponding to a more concise and convenient algorithm. What is the global social basis? Its goal is we want to find a new generator set of a given ideal. Example, given an ideal x plus y minus 1 and x plus 1 plus y plus 1 in this range. Does 4 9 in it or not? And does x plus 1 plus y 9 in it or not? Given two polynomials f and f prime in Kx, which is a free associative algebra over a field K, and we own a set X and a term order on Kx. We see that f reduces f prime to f double prime, where f prime is reduced to f double prime by f if f prime and gamma f delta have the same leading word according this term word and f double prime equal f prime minus k gamma f delta, where gamma and delta word and k in k, and it is denoted by f prime reduced to f double prime by f. Example, x2, y2 minus 2 equal xy2 minus 2 minus x yx2 minus x y2 means xy2 minus 2 is reduced by yx minus x2 y2 minus 2. Then let Q is a subset of Kx. Given a polynomial f in Kx, we see that f is reduced to f prime by Q and we denoted it f reduced to f prime by Q if there exists some polynomial Q1, Q2, and to Qn reduce f to f1, f2, fn, that's f prime, where qi in Q. This f is reduced to some reduced to another polynomial by a set. Let be a set of polynomials which generate the ideal I of Kx. Then following statements are equivalent each other. First, B is the global Shirshov basis of I. 2. A polynomial f is in I if and only if f is reduced to 0 by B, by the set B. 3. Any composition of two polynomials in B is reduced to 0 by B. That is
what do you mean by composition? Excuse me.
What?
What do you mean by composition? Excuse me.
The composition of two polynomials is here. For any given two monic polynomials f and g in a ring, the composition of f and g is a set. Okay. If the polynomial a and b in R such that f the leading term of f product B equals A product the leading term of G. This the word polynomial in the set contains the word this polynomial, and if leading term of the polynomial f equal A product the leading term of the polynomial G product B, this f minus A G B. This two set contains the polynomials like this. Then the ideal have a global basis x plus y plus 1 and 2. This set to given the two words give the same element in group in the group X R if and only if they are reduced to the same element by global Shirshov basis of ideal generated by R minus 1. The R in the room R. This means they have the same reduced form. Consider the braid group being in the Artin-Garside generators. Then Bn can write as a semi-group. Here, As plus Ak minus equal Ak plus the product As if S minus K more than 1. And let us what these generators delta delta inverse 1 less than delta. What?
Okay. 对。好。
And what this generators the inverse of delta less than delta and less than A1 and less than A2 and AN minus 1. We order words in this alphabet in the next way, comparing two words first by the degree and then the next graph when the degrees are equal.
Okay.
What?
Okay, let's go on.
Okay. Consider the polynomial ring R equal the polynomial ring R generated by the inverse of delta and A1 to AN minus 1. We have that alpha equal beta in Bn. This means alpha minus beta equal 0 in the R quantity I. This means alpha minus beta in the ring I. In the ideal I, where I is the ideal generated by the set X minus. That's the relation of the Bn. So for any given two, for any given two monic polynomials f and g in R, this is the definition of the computation of f and g. That I said. Then for the set X, if any computation of two polynomials in X can be reduced to 0 by X, we say X is the global Shirshov basis of the ideal I. If in some computation of two polynomials in X, there exists a polynomial H0 cannot be reduced by cannot be reduced to 0 by X. We add H0 to X, we get a new set X1. Then we continue this. If any computation of two polynomials in X1 can be reduced to 0 by X1, we say X1 is the global Shirshov basis of the ideal I. If not, that means there exists a polynomial H1 can be not reduced to 0 by X1. We add this polynomial H1 to X1. We get a new set X2. Finally, if for some m, in for some m inter m, any computation of two polynomials in Xm can be reduced to 0 by Xm. We say Xm is the global Shirshov basis of the ideal. We use this method to compute the global Shirshov basis. That's the Bokut in 2008. He gave a global Shirshov basis of bn plus 1. Like this global Shirshov basis like this. S1, S2, S3, S4, S5, and S6, something like this. We will use it to get a to compute the normal form of the element in Bn plus 1.
So let's look at S3. So what is V here?
Oh,
so we have S1 and S3, which are not very much easy to understand.
V1 and V2.
Yes.
Oh, oh. I'm sorry. This paper is not in this computer.
No, I don't understand. Maybe you can draw the pictures so that people can understand what is meant here by, so in S1 and in S3. So other things are just group relations, but S1 and S3, what do they mean? S1 and S3, please tell us what they mean. I don't understand the letter V, and I don't understand the letter W.
W is
just give the definition.
Can use first we have the set of the relations of Bn plus 1.
No. Please write the definition. I don't see the definition of V, and neither I see the definition of W.
The set this
I don't see any V here.
Yeah. Wait a moment. Oh. This in this paper.
So if you don't want to use this theorem of Bokut, we can say, okay, something was found. But if you do want, okay, let's look at V and W.
Here.
So what is SGP? What is SGP?
What?
What is SGP?
Seminar group. The semi group.
Okay.
It is not the group.
Fine, thanks.
Yeah. Then I will introduce the conjugacy problem of Bn. For any two given words, f and g in Bn, f and g are conjugate if there exists gamma in beta with gamma in Bn such that f equals the inverse of gamma and times g times gamma. The conjugacy problem of Bn is that in this problem, for any two given words, f and g in Bn, that there exists a feasible way to judge whether they are conjugate in Bn. Example, given two words, f equal a2 times a2 times a2 and times a2 a1. J equal a1 times a2 times a1 times a2 times a1. Thus, f and g are conjugate in B3. In fact, by this theorem, we can see f is a normal form, but the normal form of J is a1 times a1 times a2 times a1 times a1. They are not equal in Bn. But I wonder that f and g are conjugate in B3.
Excuse me. Is there a screw at the center of Bn?
What?
Is there a screw at the center of the braid group?
Oh, I don't know the center. How to use in this?
The generator of the center.
This center.
I think that the screw generates the center of the braid group.
maybe the center cannot solve this problem. In fact, Garside, Berman, they solve this problem use a set and fundamental word delta. What only center I think cannot solve.
But I checked for n equals 3 and 4, data square is the generator of the center.
I'm not here, but I can't hear. I can't. I'm sorry. I can't hear what you say.
I mean the delta square, the bit delta square.
Delta.
It generates the center.
Artin paper gave the center, the generator of the center.
Yes, I know. I mean, it's exactly the same as delta square.
I have no idea.
Oh, okay, thank you.
Oh, I'm sorry. Garside obtained an algorithm of the conjugacy problem of being with the fundamental word delta, and then refine and Merton improved the Garside conjugacy algorithm by using a much smaller finite subset of each conjugacy class. Berman, Korn, and Lee provided a new and very natural set of generators for Bn. And these new generators need to a new and shorter fundamental word delta with replace Garside's fundamental word delta. The solution was simpler than the Garside. But one of these solutions used the combinatory. In comparison, the algorithm based on global Shirshov basically more constraints. That's why I choose the global Shirshov based method to solve the conjugacy problem. let R equal semigroup N with the generator, the inverse of delta and delta A1 and A2. Consider a automorphism map. A map R to R and X to R satisfies a map inverse of delta to inverse of delta and delta to delta, and map A1 to A2 and A2 to A1. Then we get this theorem. Give F and G in B3, then F and G are conjugate if and only if F minus G in H, and H is a additive subgroup of the game R generated by Q. And R is this semigroup. Q is a set. This conjugate relation, and this is relation is this map, and the relation corresponding to the to T. T is the global social basis of B3. This proof in the paper. In the paper, I joint work with this with Professor Norfei Liu. Then we choose a global social basis of B3, T1 and T2, T3, T4, and T5. All of these sets are finite, so we can easy to compute the global social basis. There is not the same way. This computation of these two polynomials f and g in Q is not the same with the computation of the two polynomials in the ring R, because Q contains a relation. This is conjugate relation. They count times another polynomial. So this definition of the computation of two polynomials is not the same with the that one. We choose two polynomials f and g in Q. The computation f and g it is defined like this. If if LGF is not the same with LTG, the computation is empty. Only if they are LTF equal LTG, we have the not empty set, the F and F minus G. We call it the computation of F and G. Then for the set Q, if any computation of two polynomials in Q can be reduced to 0 by Q, we say Q is the global social basis of the additive subgroup H. If for two polynomials in Q, the excess at polynomial H0 cannot be reduced to 0 by Q, let Q1 equal Q unit H0. That means we add the polynomial H0, which can't be reduced to 0 by Q to Q. Then we get a new set Q1. Then if for the set Q1, any computation of two polynomials in Q1 can be reduced to be 0 by Q1. We say Q1 is the global and social basis. If not, the excess polynomial H1 cannot be reduced to 0. We add this and we add the polynomial H1 to Q1. We get a new set Q2. Finally, if for some m, the polynomial in computation, if it is not empty of any two polynomials in Qm can be reduced to 0 by Qm, with Qm is the global Shirshov basis of the additive subgroup H. It is also called a global social basis of conjugate classes of B3. To use to compute this global social basis of conjugate classes of B3. The theorem, a global social basis of conjugate classes of B3 consists of the following relations: G equal T and S, where T equal T1 to T5, and S equal SC and SE1 and SE2 and SO1 and SO2. That's T1 to T5. T is corresponding to the global Shirshov of B3, and S is S is the conversion of the element in Q. I will introduce the the proof. We just need to verify that for any two polynomial in G is T and S. The global social basis of this of conjugate classes of B3. Only the polynomial in computation of them can be reduced to 0 by G. In fact, for any two polynomials f and g in G, the computation f and g is empty or contains only one polynomial f minus g. If f in Ti and g in Tj, this means f and g come from the global Shirshov basis of B3. The polynomial in this computation of f and g can be reduced to 0 by t, because t is computation to a global Shirshov basis of B3. Then that means we need to verify that for any polynomial f in S and any polynomial g in G, the polynomial in computation of them can be reduced to 0 by G. This verification process is too cumbersome to show here. It is in the paper. It is in the paper is such like this. We suppose G is G in SC and G2 in T1. And this G1 in S or SE1 and G2 is in T1. This global Shirshov of the conjugate classes of B3 is corresponding a algorithm for the conjugacy problem of B3. For any given word f in F, if there exists R in this F in R. If there exists R in R such that F can be reduced to R by G, and G is irreducible, we call R a conjugate normal form of the word F, denoted by CNF F. In fact, by the theorem, we get a new algorithm for the conjugacy problem of B3. First, for any given two words F and G in R, reduce them by the basis G and get the conjugate normal forms CNF F and CNFG we compare this we can compare this to conjugate norm form CNFF and CNFG. We have that CNFF equal CNFG if and only if F and G are conjugate in B3. Example, given two words F equal A2 4 times A1 and J equal A1 times A2 times A1 times A2 times A1. It is clear that F can be reduced by SC to A1 4 A2. And then can be reduced by S E2 to delta A1 2. And this is it is G irreducible. Then it is the CNFF. Similarly, G can be reduced by T2 and then reduced by SC and then reduced by SO1 to delta A1 2. It is easy to check that F and G are conjugate in B2 because CNF is equal to BQ CNF G. In fact, let H equal delta A1 2. We have that the inverse of H times F times H equal G in this way. Thank you.
Okay, thank you for your talk. Dear colleagues, please, your questions or unmute your microphones or write your questions on the chat line. Maybe any comments or remarks?
Well,
we still have some time. Maybe you can comment a little bit on your S. So we had two sets of relations, T and S. So maybe you were too quick in talking about S. Have you heard my question?
Okay. I can try to solve this. This set T. This set T is here, which
yes,
we choose. S is the this set this. Hey, it is computed by the computation of the computation of the polynomials in Q. This is the conjugate relation.
Okay. Dear colleagues, any more questions, remarks, comments? Well, Son John, do you have any question?
Oh, no, thank you.
Okay, if it's not the case, so let's thank the speaker again. Okay.
Thank you. I'm too slow.
Okay. So that's all for today.